In the age of scientific exploration in the 19th and early 20th centuries, the atom, the very building block of the universe, was caught in a paradox. According to John Dalton's modern atomic theory, atoms were seen as indivisible and eternal. Yet, curious experiments with cathode ray tubes and radioactive particles painted a different picture, revealing atoms as complex structures composed of positively charged atomic nuclei and negatively charged electrons. But how could these atoms remain stable with such opposing forces at work? The answer lies within a groundbreaking principle that forever changed our understanding of the universe. And the key to this enigma is, well, I promise you, you'll be quite intrigued to hear all about it very soon. We'll dig into the atomic depths of this mystery together. Stay tuned. What's up, my amazing and curious folks? Are you ready to unravel another mystery with us? I'm your host Cesar Chagas, and joining me today is the ever-insightful Sonia. Strap on your seatbelts and get ready for a journey into the heart of the atom. And don't forget, hit that subscribe button and the bell icon so you never miss a moment with us.
Hi folks. Thrilled to be here and dive into this atomic adventure with you all. You're in for a treat, I promise.
Let's dive a little deeper into the heart of the matter, literally. In the 19th and early 20th centuries, scientists were grappling with a peculiar paradox concerning atoms. The atomic theory put forth by John Dalton in 1803 proposed that everything was made of indivisible atoms. Each atom of the same species was identical and had the same properties. But experiments with cathode ray tubes and radioactive particles painted a different picture.
Wait, so the idea was that these atoms were indivisible, but then they found out they actually had parts?
Precisely. These experiments revealed that atoms were composed of positively charged, massive atomic nuclei and negatively charged, light electrons. This instantly created a paradox because according to the laws of electricity and magnetism, these atoms should be unstable. They should collapse in on themselves in a fraction of a second.
But that doesn't happen, right? I mean, we're all here and not collapsing into atomic dust.
Absolutely correct. Atoms are observed to be stable, and they make up all of our tangible reality. But this raised a big question. How did physics save the atom from this catastrophic fate?
I bet it wasn't as simple as they just do, huh?
Haha, you're spot on. The answer lies in a principle known as the Heisenberg uncertainty principle. This principle not only saved the atom, but also allowed us to predict their sizes.
So, the answer to this big atomic mystery was uncertainty? That's a bit ironic, isn't it?
It is indeed. But it's this very uncertainty that reveals the intricate and fascinating behavior of the atomic world. A world we're about to delve deeper into. Stick around. To understand this quantum puzzle, we need to go back to the late 19th and early 20th centuries. Experiments involving combustion, oxidation, and reduction had disproved many alternative theories of the material world. Things were looking great for our understanding of reality as being composed of atoms. However, an experiment by J.J. Thomson in 1897 changed everything.
Another twist in the plot, huh?
Exactly. Thomson's experiments with cathode rays showed that atoms were not indivisible, as initially thought. They had parts to them.
Can you explain what a cathode ray is?
Sure, imagine a glass tube from which most of the air has been removed, creating a near vacuum. At either end of the tube, you have two pieces of metal, or electrodes. One electrode is positively charged, known as the anode, and the other is negatively charged, known as the cathode. When you apply a high voltage, a stream of particles moves from the cathode to the anode. This stream is what we call a cathode ray.
So how did these rays help Thomson prove atoms have parts?
Thomson fired these cathode rays at an electroscope, which measures electric charge. The electroscope charged up, demonstrating that the particles fired off by the cathode rays were electrified, or in other words, carried a charge. What's more, these particles could be deflected by a magnet, and the direction of their deflection showed they carried a negative electric charge.
So this was the discovery of electrons?
Precisely. Thomson's experiments revealed that atoms themselves contain these negatively charged, very low-mass constituents, which we now know as electrons. It was a significant step towards our understanding of the composition of atoms and the existence of subatomic particles. Now that we have this understanding of electrons, we must ask, what else is inside an atom? Since atoms are electrically neutral and much more massive than an electron, there had to be some other particle inside an atom. This was uncovered in 1911 through the experiments of Ernest Rutherford.
So, what did Rutherford do to uncover these other particles?
Rutherford's experiment was deceptively simple, but incredibly illuminating. He used a ring-shaped apparatus designed to detect particles coming from any direction. In the center of this ring, he placed a very thin foil made of gold. This foil was so thin that it was probably only a few hundred or thousand atoms across. Then, he bombarded this foil with radioactive particles from a particular direction.
So, he was just trying to see what would happen when these particles hit the gold foil?
Exactly. The expectation was that the emitted radioactive particles would pass right through the gold foil, much like an elephant would charge through a piece of tissue paper. However, this wasn't exactly the case.
Interesting. So not all the particles just passed through?
That's right. A small but significant number of particles did not just pass through. They behaved as if they had hit something hard and immovable. Some scattered off to one side or the other, while others seemed to ricochet back towards their direction of origin.
So, what did this mean for the understanding of atoms?
This experiment provided the first evidence that the inside of an atom wasn't a solid structure as previously envisioned. It suggested that an atom consisted of an extremely dense, small core and a much more diffuse outer structure. To put it in Rutherford's words, the result was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So, Rutherford's model, as elegant as it was, had a fatal flaw. Just like planets orbiting a sun, he imagined electrons orbiting the atomic nucleus. But an electron is not a planet. It's negatively charged and the atomic nucleus is positively charged. According to classical electromagnetism, an electron in orbit should radiate energy away, causing the orbit to decay and the electron to spiral into the nucleus. This model was unstable, and Rutherford knew it.
Quite a dilemma, isn't it? This actually reminds me of a childhood moment. When I was a kid, I had this little solar system model in my room, planets orbiting around a glowing sun. I remember one day, the string that held my mini Mars snapped, and it fell right into the sun.
That's a great analogy for Rutherford's predicament. In his atom model, electrons were like your miniature Mars, destined to crash into the nucleus. But in reality, atoms are stable, so something else must have been at play.
Right. So, how did scientists resolve this paradox?
Well, it took the work of Niels Bohr and the development of quantum mechanics to correct Rutherford's model. Bohr introduced the idea that energy levels in atoms are quantized, that is, electrons can only exist at certain energy levels. This prevented them from spiraling into the nucleus. However, even Bohr's model had its shortcomings. The true key to understanding the stability of atoms came from the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics. But that's a discussion for another time.
I guess my miniature solar system needed some quantum mechanics to keep Mars in orbit, huh?
It seems so. Quantum mechanics has a knack for turning our classical understanding of the world upside down. This brings us to the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics, discovered in the 1920s. There's always an inherent uncertainty between complementary quantities in physics. The more accurately you measure one, the more inherently uncertain the other gets.
I remember, as a kid, trying to catch fireflies in the dark. It felt almost impossible to track their exact location and predict their next move simultaneously. You could either know where they were or where they might go, but never both accurately at the same time.
That's a perfect way to describe it. The most famous example of this principle is the position-momentum uncertainty relation. No matter how well you measure the position and momentum of a particle, the product of their uncertainty is always greater than or equal to half of the reduced Planck constant.
So, does this principle apply to atoms as well?
Absolutely. Using this uncertainty relation, along with the knowledge that atoms are made of positively charged nuclei and negatively charged electrons, you can derive not only the stability of an atom, but the physical size of an atom as well.
So, it was like those fireflies, carrying their own little secrets, were teaching me a profound lesson in physics all those years ago.
It seems they were. The complexities of the natural world often mirror the complexities of physics in very poetic ways. So, let's delve deeper into the hydrogen atom, the simplest atomic case. We're going to use three equations to explain the nature of this atom, including Heisenberg's uncertainty relation for position and momentum.
Hold on. We're entering the realm of math now, aren't we?
Yes, we are, but don't worry, we'll break it down. The uncertainty relation is that the product of the uncertainty in position and momentum is always greater than or equal to half of the reduced Planck constant.
Okay, so that's our first equation. What's next?
The second equation is about the electric potential energy of the electron in the vicinity of a proton. It is determined by the Coulomb constant, the charge of the electron, and the distance between the electron and the proton.
Makes sense, considering the charge interactions within an atom. And the third equation?
The third relates to a particle's momentum and its kinetic energy. We can assume that the particle is non-relativistic in this case.
And how do these equations come together?
When we balance out the electric potential energy and kinetic energy and apply the uncertainty principle, we can derive an equation that gives us an approximation for the distance between the nucleus and the electron in a hydrogen atom.
And that would be the size of the atom, right?
Exactly. The estimated distance is about 1/10 of an angstrom, which gives us an idea of the physical size of a hydrogen atom.
So, it all comes back to the uncertainty principle then?
Indeed, the mysteries of the atom and its stability are rooted in quantum mechanics and the uncertainty principle. The Heisenberg uncertainty principle doesn't just provide us with insights into the nature of atoms and their stability. It also explains why atoms don't collapse and have their electrons spiral into their nuclei. As the distance between the electron and the nucleus becomes smaller, the momentum becomes less certain. And when that distance is squeezed to a smaller value, the uncertainty principle forces the momentum to rise.
So, the increase in momentum actually prevents the electron from falling into the nucleus?
Indeed. This increase in momentum causes the electron to move faster, which avoids the electron falling into the nucleus. This is a key mechanism of quantum mechanics that keeps atoms stable and prevents a classical catastrophe from occurring.
Fascinating. Is there more to this quantum mechanics story?
There certainly is. It also introduces the concept of zero-point energy. There's a lowest energy state in a quantum mechanical system, and it's not necessarily zero. It could be positive and non-zero, like in the case of electrons bound to an atomic nucleus.
And what does that mean for us, or for the universe?
It implies that you can't simply extract energy from the quantum vacuum as it's already in its lowest energy state. There are no possible decays from this lowest energy stable state. So, any system of quantum particles will have a lowest energy state, all determined by the fundamental principles of quantum mechanics. This includes, of course, our humble atoms, which owe their stability to the uncertainty principle. Today, we've embarked on a journey to understand the stability of atoms, those tiny building blocks of matter we learned about in school. The answer to this mystery lies in the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics. The more we try to squeeze the electrons closer to the atomic nucleus, the faster they move, preventing them from spiraling into the nucleus. Thus, the atom remains stable and does not collapse.
That's right. And it doesn't end there. The uncertainty principle also introduces the concept of zero-point energy, a lowest possible energy that a quantum mechanical system can have. This not only underpins the stability of atoms, but also of the universe as a whole.
So, next time when you look at anything around you, remember the Heisenberg uncertainty principle is working tirelessly to keep the atoms in it stable.
That wraps it up for today's episode of Curiosity Wonderland. If you enjoyed it and had an aha moment, don't forget to give us a thumbs up, share your thoughts in the comments section, and share this episode with your friends. Let's spread the knowledge.
Yes, we certainly value your support. Keep your curiosity alive, and we'll be back with more interesting mysteries soon. Until then, take care.
Bye everyone, and stay curious.
Our deep dive into the quantum world today was inspired by the article How Quantum Uncertainty Saved the Atom written by Ethan Siegel on the Big Think site, published on October 5, 2023. If you want to explore this topic further, you'll find the full URL in the video description. Now, I'll sign off. Take care, everyone.